Okay, so for this video we're going to look at the design of the power amplifier. I'm going to make it across 3 stages, and I'm going to look for something around 6 watts. I don't think I'm going to get that with the BD139s that I'm going to use, but hey, that's something to aim for, and if it's in the vicinity of 5, then I'd be quite happy with that. So the overall gain is going to be 10 log 6 over 1 milliwatt. We're going to have about 1 milliwatt coming in from our mixer, which gives us an overall gain of around 37.8 or 38 odd dB. So we'll split that up into approximately 13 dB for stage 1, which will give us 20 milliwatts out, 10 dB for stage 2, 200 milliwatts, and then finally roughly 15 dB to get us up to around that 6 watts. But again, we'll see if we can actually make that happen. For stage 1 and 2, with the common emitter type arrangement, we're going to have a collector swing of around 10 volts peak to peak. So for stage 1, volts times current equals power. So if we convert that 10 volts peak to peak to RMS, so divide by half, then multiply it by 0.70. That's wrong. It should be 7071. We get 5.7 milliamps. So I'm going to double that. So we're going to have a quiescent current through stage 1 of 10 milliamps. Gosh, I got that wrong. For the second stage, we're looking for that 200 milliwatts. Again, 10 volts peak to peak, so we're going to have around 57 milliamps, so I'll have a roughly 100 milliamps quiescent current flowing through that second stage. So for stage 1, again, it's the common arrangements I've been using in the past. Common emitter, we've got the primary for the coupling transformer in series with the collector, with a 10 ohm resistor there just to provide some isolation from the VCC rail. As we talked about here, we want to have IDC of 10 milliamps. Rule of thumb, we're going to have the emitter voltage about 1/10 of VCC. The AC voltage gain at 3.7 megs, so 300 divided by 3.7 equals 81, and then our DC voltage gain of 100. Current gain. So again, same maths as we've seen in the past. Our emitter resistor will be the voltage divided by the quiescent current. Gives us 120 ohms, which is a standard value, so we'll use that. R2 here, again 1.2 plus 0.7 divided by 10 times the base current. So we've seen that before. Comes around at 1900 ohms, so we'll use 1800. R1, same as we've seen in the past. Comes out at 9090, so we'll use 8200. And then we need to start to work out what our load's going to be. So the load that this collector wants to see to generate 200, say again 20 milliwatts, will be VCC minus VE all squared divided by 2 times power out. So 12 minus 1.2 approximated squared divided by 2 times 20 milliwatts gives us that 2916 ohms. So that's going to be what we're going to try and present to that collector with that transformer up here. So for T1, so that's our first transformer here, which is coupling in our 50 ohms and matching that with our input impedance. Again, I should caveat this, right or wrong, these are the calculations I use. They're not necessarily 100% correct, but they seem to work for me, so until I read something a bit more clear, that's what I'm going to stick with. So as we said, matching our 50 ohms with Zin, where Zin is approximately R1 in parallel with R2, and parallel, because this is unbypassed, with beta brackets little re plus our emitter resistor. And if we substitute in all the values, 8200, our 1800, our AC beta of 81, 26 millivolts for our normal temperature, over 10 milliamps plus 120, all works out to be 1285. So then we can work out our turns ratio. So 50 times the turns ratio squared needs to equal 1285, which gives us an N of 5.06. So we'll use 25 to 5, which is about right. Remembering our rule of thumb that we want to have the inductive reactance to be roughly 4 times the impedance on either side, and that's what these little values down here are, which are approximately about right there. So yeah, close enough is good enough, so we'll run with that. So that's the values we'll use for stage 1. For stage 2, again, same setup, but we're going to have significantly more current this time. So we talked about having 100 milliamps flying through here. That's going to be too much for the dissipation of a 2N3904 like we used for the first stage. So for this second stage we'll use a BD139. DC current gain of 200. It's got a power dissipation factor of 12 watts, which is good. That's more than enough for us. Bearing in mind, this is going to be a Class A amplifier, so it's only ever going to be 50% efficient. So if we want to generate 200 milliwatts out, then we're going to be burning 200 milliwatts. It's got a collector emitter breakdown voltage of 100 volts, which is good, and then our AC 250 divided by 3.7 megs gives us 68. So running through exactly the same maths, noting that we wanted to make the quiescent current through here 100 milliamps. We can now go through using our rule of thumb to work out our emitter resistor. Exactly the same maths as we've seen before to work out our R2, this one here. Came out at 380, so we'll use 390. For R1, came out at 1654, so we'll use 1800. And then same again to work out for the second transformer up here when we get to it. Our desired load, again VCC minus VE squared divided by 2 times power out. Substitute in our values, in this case 200 milliwatts gives us a desired, or what we need to present to that collector, 292 ohms. So T2 now, so T2 is the transformer that's going to match stage 1 with stage 2. If you recall, we said on stage 1 that we wanted to present to its collector 2916 ohms. So we now need to match that to our Zin for this stage. As we've seen in the past, with this particular configuration here, R1 in parallel with R2 in parallel with beta brackets little re plus re, because nothing is bypassed. Substituting all the various values, comes out at 230 ohms. So if we work it out, our N squared, or our N is going to be 3.56 to match that 230 with the 2916. And for now I'm going to use 13 to 4. It's a little bit low on the inductive reactance. We could have gone up to 35 to 11, which would have been better, but I just don't particularly feel like winding 35 turns at this stage of the game. I'm just going to try our 13 to 4 and we'll see how well it performs in the circuit. So that's stage 2. Right, so for stage 3 we're going to use a push-pull arrangement. We're going to use 4 BD139s, 2 on each side in parallel, and that's going to be driven by a transformer here with a split secondary to provide that antiphase for the bases, and then that's going to be recombined with a similar style transformer on the output to recombine those two halves then to match through to our 50 ohm load. The biasing on the base is effectively voltage divider biasing. It's just sitting up here. Because this is DC, whatever voltage we have here will be presented there and there, which is directly onto the bases. So if we take this point up through here, we can see here what is traditionally our R1, and down here is our R2. R2 in this particular case is a 4001 power diode, which is forward biased, and then the current that flows through that is, because it's regulated, will then provide by varying this resistor here, which we'll see later on once the circuit's made up, will then set the base current, which then through the amplification will then provide our quiescent current. So that's a variable. We'll start off with a 5k trim pot, work out what it needs to be, and then we'll throw a permanent resistor in there. On the output side, we need to provide VCC to the collectors, and that's done through that center tap, same style arrangement. Anything we see here gets fed straight through to the collectors. So we come up here, we want to provide that VCC, or that 12 volts, but we want to make sure that we don't have any RF coming through, so we'll use a radio frequency choke. That'll be a standard one. We'll use an FT37-43 with 10 turns. Probably 22 gauge, I guess, for the current going through here. And then we'll decouple both sides of that RFC with at least a 100 nanofarad capacitor. Then on the VCC side, for good measure, we'll throw a 100 microfarad capacitor in there as well. Yep, so that'll be essentially the biasing for that system there. So just going through, making sure that we've got the right devices for this amplifier here. Let me just pull that down just a tad. Again, this is going to be class AB, so we're going to have just a little bit of current flowing through these both sides of this in the non-signal, or the no input state, and that's going to be 10 milliamps, which will provide us enough for that. The BD139 can dissipate 12 watts, which is good, so that's greater than 2 times our power out, so that's a big tick there. Our FT for this device is, now what's that FT? It's right up there. It's certainly much greater than, certainly 5 to 10 times 3.7 megs, or the highest frequency we'll get out of this will be 3.9 megs for the 80 meter band. So the FT, oh gosh, I think it's 200, is certainly greater than that, which is good. VCE 100 volts, which is good, so that's greater than 2 times 12. And what I haven't drawn here, and I may consider just for safety measure, is having a couple of Zener diodes, probably sort of around that 40 volts range, which in normal operation won't be triggered, but should for whatever reason we lose our load and we have a huge impedance mismatch, rather than having the voltages going right up and potentially damaging these, we can have those Zener diodes there. So I haven't drawn them here, but I'll probably consider putting them in, if not this radio, certainly the next. Again, our AC current gain, so 250, that's our gain bandwidth value, divided by 3.7 megs gives us 68. And as we said, we want to set the quiescent current with no signal at 10 milliamps to give us that class AB. So it's going to be a push-pull arrangement, so the desired load that these transistors want to see on each side. Again, our standard formula, VCC minus VEE all squared over 2 times power out, so we can substitute it in. VCC, so 12 volts minus, and our emitter voltage will be 10 milliamps times 1 ohm, all squared over 2 times 3 watts, because remember we want to do 3 watts either side to give us a total of 6 watts. Again, not going to get there, but we'll give it a go, and it comes out to be roughly 23 ohms per side. So for T3, which is the transformer which is matching the load of stage 2 with the input for stage 3. So we're matching our 292 ohms from the previous stage as a desired load through to our input impedance. Right or wrong, I've said it a few times now, I'm no expert in this field, but it seems to work for me. The calculation I'm going to use is beta little re plus re, substituting in our values, comes out at 244. So 292 to 244 is roughly 1.1, and that's pretty close to 10 to 8. So I'll use that. It's a nice easy one to wind. So that's going to be 8 turns on the primary, and then 2 10 turns with a center tap. So that presents the correct impedance for each side, and also gives us that center tap to give us that anti-phase drive for that push-pull arrangement. And then the final output transformer, we talked about the 23 ohms per collector. That's what the collectors want to see, and matching through to a 50 ohms total on the output. So that's pretty close. We sort of round that to 25 ohms. 25 plus 25 equals 50. So the output transformer total will be approximately 1 to 1. So what I'm going to do for that, I'm going to use 4 turns and then 8 turns on the secondary. So 4 turns, so 2 lots of 4 with a center tap, so we can recombine that push-pull arrangement, and then, like I say, 8 turns on the secondary, and round numbers at 3.5 megahertz, which is our lowest frequency. That gives us around 500 ohms, which is good, because that side's 50, 4 5s are 20, so we're more than our rule of thumb there. So that's essentially what we're going to try and build up now. So let's go ahead and solder that up, and then we'll break the video after each stage is built, and we'll look at how that stage is performing, and then we'll go on to the next one. So what I'll plan to do is I'll build up stage 1 for a start, and then I will look at the calculated input impedance for the next stage, and I'll just have that as a simple resistor with no second stage, and then we'll look at how that performs, and then we'll do the same with the combined first and second stage, again looking at what the input impedance would be for this one hanging here, and then once we have all 3 stages together, we'll then throw that into the actual circuit itself, put on a proper 50 ohm load, dummy load that is, and we'll see how that looks. Right, so let's break there, and we'll be back shortly. Okay, so we've now soldered up the first stage. You can see there the 3904, and what I've decided to do just for testing purposes is the emitter resistor I've replaced with a 1k ohm trim pot. I've only got 10 milliamps flowing through here, so I'm pretty happy I won't burn that out. You can see our input coupling gain transformer there, so that's bringing our 50 ohms up into our input impedance of 1200 ohms, and then we have that T2, that output transformer, which is transforming our load, or in fact it's transforming the second stage Zin, which is approximately 230 ohms, which I'm simulating here with a 220 ohm resistor, transforming it back up into our desired load for stage 1, which was approximately 2916. So that's using that transformer turns ratio of 13 to 4 there. So as you can see here, we'll just go up onto the scope. So that there is the output. So at the moment the output is reading 1, 2, 3, 4, 5, 6, 6 at 1 volts, so that's 6 volts out, for 0.63 volts peak to peak in. So 0.63 volts peak to peak across 50 ohms is 1 milliwatt, and then 6 volts peak to peak across that 220 ohm load resistor turns out to be 20 milliwatts. So we're getting our desired 13 dB gain there. So if I just adjust that variable resistor we saw down there for the emitter resistor, we can see there we can quite simply adjust the gain of that particular stage. So I'm going to adjust that for 6 volts peak to peak, like I say, which turns out to be a stage gain of 13 dB, which is our desired gain for this particular stage. So next steps will be to now solder up the second stage, and we will then remove that simulated input impedance for the second stage, build the second stage in here, and then do a similar test, and we will measure the output of that second stage. Right, the next stage is second stage has been soldered up. We can see here the BD139. We're using that because we've got roughly 100 odd milliamps flowing through there, which I'll put a small heat shield on in a sec. Which is too much to have another second 3904. So the BD139's there. Through LT Spice, the best configuration for the feedback on this circuit was to have a series capacitor and resistor. I'm using a 1k ohm resistor there, feeding back from the collector back through to the base. It's a little bit untidy there, I'll tidy that up, but that's just for testing purposes. And in the load for the BD139, it's wanting to see a load of around 292 ohms. So we got our transformer there, which is transforming what will be the input impedances of the push-pull amplifier, which happens to be around 450 ohms. So I'm just using two 470 ohm resistors to simulate that input impedance for stage 3, just being transformed back to present around the right type of load. So it's about right for the collector on this BD139. So at the moment, if we look at the output, so I'm just scoping across one of those resistors, which remember will be the input impedance for the stage 3. So there I've got an output of roughly from 5 volts per division, so 5, 10, 15, 20 round numbers. So 20 volts in, and our input is sitting on a roughly, sorry, that one there, we're on 1 volt divisions, so 1, 2, 2.6, so 20 divided by 2.6, enter, log 20 times is giving us around 8.2 dB gain. Let's just do that again. So that's 20 volts. What did we say here? That was 1, 2, 2.8. 2.8 divide log 20 times. Sorry, my apologies. That's actually 17 dB. I didn't think 8 sounded right. So we've got there way more gain than we need. So what we can do now, so just going back to channel 2, which is the output, which is the input to stage 3, and you can see there if we adjust, which I'll do now, that feedback resistor between the collector and the base, we can adjust gain on that, so we can bring that back down to our desired on or about 10 dB gain. So we'll adjust that once stage 3 is in, and we'll go from there. This will be quite useful because what I'm thinking about doing is running the push-pull amplifier on stage 3 at a higher VCC rail. So I'm thinking about, if we just come back down to here, I'm thinking about running stages 1 and 2, these two stages here on 12 volts, and then stage 3, which is the push-pull, running a VCC rail of potentially I don't know, 15, 16, 17 volts around there, to give us a greater swing. But we'll just play that by ear at this stage. So that was I was just tweaking that resistor there just to adjust the output gain across the simulated input impedance for stage 3. Anyway, so that's stage 2 done, and now we'll solder up stage 3, and we'll see how that performs. Right, so the third stage is built. So just recapping, we've got a push-pull arrangement here. We've got 2 on either side BD139s running in parallel, being driven by a transformer here which has 10 turns or 8 turns on the primary, and then 2 10 turns with a centre tap on the secondary, which is providing that anti-phase for the push-pull amplifier. That's been combined again in another split primary transformer here on a large toroid with an 8 turn secondary. So that's transforming on the second one here that 50 ohms back through for a desired 25 ohms per side for the 2 BD139s, and then on the input side, that amp, we've got that matching the 450 odd ohms on the input here through the desired the 292 odd ohms that this BD139 here wants to see. We can see if we just zoom up a little bit, that's going to focus hopefully. And we'll look at the circuit again. That diode there is it's a voltage divider biasing essentially on the center tap from here, but in this case R2 has been replaced by a 1N4002 or 4001 sorry diode, which is providing approximately 0.7 volts on the bases of the 139s, and then there's a 2k ohm resistor here which sets the bias current for around 10 milliamps. So the quiescent current is 10 milliamps. And then just decoupling that point there, we've got 100 nanofarad and a 1 microfarad capacitor. On the output side, that center tap there, the output of that is VCC through a RFC. That's a FT37-43 with a standard 10 turns, so quite a common RFC for HF. With that point there also decoupled with another 100 nanofarad capacitor running through to earth. So yeah, so that's basically how it is. And what I've elected to do is put it into the circuit. The board itself is a bit of a dog's breakfast at the moment, but it's more just for experimenting. So just to sort of recap what we've currently got here, we've got the that relay now is providing some switching for the two IF filters. So if you recall, orange is for receive, yellow is for transmit. The normally closed contacts are on the outer side, and then the normally open are on the inner side. So on receive, the outer contacts are made, so RF comes in, gets mixed down to our IF frequency, comes in through this port, out there and around that way, coming in across to our product detector, and then audio coming out. On transmit, our mic audio comes in, gets mixed up to on our balance modulator up to our IF frequency, and now because this relay is made, and the inner contacts come into play, so you can see it here, it bounces across to this side, and again same loop through through the filter, and then through here to our mixer, and then as RF. So that's just quite easy way, and I've had quite good success with those in terms of isolation with that particular style. I've had really no problems that I've encountered yet with the contacts being close and having any mixing or bleed across mortar point. So on transmit, we've also got another relay sitting up here, and that's now essentially switching what happens once the RF, which has come from this last mixer here, passes through our bandpass filter. It's got a choice of either coming on receive from the antenna amplifier, which is the green wire, or it gets our on the transmit side, it sends, because it's coming through this way, sends RF through our power amplifier. Output of the power amplifier then goes through the black wire to our TR switch, and then straight out the antenna. So remember, we're using the second contact of this double pole double throw switch to be our antenna switch. So at the moment I've got just a podcast playing on the MP3 player, and we can key that, and we can turn up the volume a little bit on that. Yeah, so that's on the peaks here, we're getting just under 5 watts, so I think that's probably all I'm really going to be able to squeeze out of the BD139. The next radio is definitely going to use some higher power transistors to get a bit more oomph out. So, but this is just purely playing around here with the push-pull. So I think next steps now will be to build the low pass filter. At the moment I'm just transmitting into a dummy load there. So I'll need to build a low pass filter for the output of the amplifier here before it goes out the antenna. And then we also need to look at making up with that old meter an S meter on receive, and then also sensing this transmit power, and we'll turn that into a power meter of some sort. So we need to make that up. Then once we've got those in circuit, or at least a low pass filter in circuit, then we can go live and see if we can't make a contact. But essentially the radio is pretty well done, like I say, apart from that low pass filter. So I'll knock it on the heads there. Any questions, just sing out. Like I say, right or wrong with the design. For me it's all about trying to learn, and that's really what it's all about, just trying to understand more about HF or RF in circuits and the like. Anyway, thanks very much, and we'll see you next time for the low pass filter, etc. Until then, cheers.